all for showing up. It's a good small group, but hopefully it will be helpful for you. And my goal with this talk is basically to summarize two studies from my research, one which has previously been published and one which is currently in review, that really illustrate how contemporary statistical approaches can be used to address key issues in cognitive aging and mental health. And so this will be kind of a fast whirlwind overview, both of the methods and of the substantive aspects of the studies, but hopefully there will be some Q&A time at the end if you have more specific questions, and then we can dive a little bit deeper. But I'm always happy to go deeper at any point following this. This is really just kind of to pique curiosity and to give a sense of what is currently possible. So I'll go ahead and jump to the talk. Okay, hopefully you can all see that all right. Let me know if you can.
Looks great.
Okay, super. So the focus will be, of course, on cognition and depression associations, but also on the statistical methods. So they kind of go hand in hand. To give a broader scope for these issues, the World Health Organization has identified cognitive impairment, which includes a range of disorders from severe dementias all the way to more subtle cognitive declines. But cognitive impairment and depression are two of the more salient adverse mental health outcomes for middle-aged and older adults. Prevalence rates are notable. For the more severe cases, you might have 5 to 7% of an older population affected, but upwards of 20 to 30% in cases of milder symptoms of cognitive impairment and also depression. Cost of care is substantial, and that's just what we can measure. These have adverse impacts, not just on the individuals affected, but also on their families and societies. And these are growing issues because the global population of aging or older adults is expanding and expected to nearly double from 12% to 22% by 2050. So we're not really prepared globally to deal with some of these issues. And ideally, we'd like to aim at early detection, prevention, cost-effective care strategies. And I think the way to get at that is just through better information and then kind of thinking more critically about what we can do before these become severe enough to require hospitalization or in-home care. So in our lab, we work with this kind of broad conceptual model. You can zoom in on any of these pathways, and then a lot of the issues become much more complex and specific. But in general, we know there are both modifiable and non-modifiable risk and protective factors for cognitive decline and depression in later life. And what that means, modifiable or not, also depends on the context. But this is kind of generally the framework we're working within. So notice the bidirectional arrows linking cognition to depression. That's because these two are often cognitive problems and depression in later life are often comorbid. They're really difficult to tease apart. Sometimes it's not easy to know if one is driving the other. And we'll speak a little bit of that about that in the first study. So again, two studies. For the first one, we're really focused on cognition-depression dynamics. Dynamics means time-dependent associations between changes in cognitive status and changes in depression risk or depressive symptoms. And we get at that using this dynamic structural equation modeling framework. And then for the second study, we're really looking at depression caseness as an outcome. And we want to evaluate a number of different lifestyle, behavioral, cognitive, and biological and sociodemographic risk and protective factors, all as comparative influences on depression risk. And for that, we'll use a machine learning approach. Data for both studies come from SHARE, which is the Survey of Health, Aging, and Retirement in Europe. So broadly, there are 20 countries, 20 European countries plus Israel represented in this data set. Over 100,000 individuals who've been measured repeatedly. It's a longitudinal study with waves occurring at every 2 years. So for the first data analysis, we'll look at That focuses on share waves 1 through 6 with an N of over 100,000 folks, ages about 50 to 90 years. And for the second study, it's cross-sectional. We're really focusing on wave 6 because they have a number of social variables that were only available at that wave that we were interested in looking at. Share, the data for share usually come from telephone surveys or computer-assisted personal interviews. The cognitive measure we'll focus on in these two studies is delayed recall memory. So basically, share participants during the phone interview were asked to remember a 10-item word list. The interview proceeded, and then 15 or 20 minutes later, they were asked how many of those words they could recall, and that was their memory score. And then depressive symptoms were ascertained by the Euro-D inventory, which has been validated across a number of European centers with high reliability. Scores on that greater than or equal to 4 roughly translate to clinically meaningful diagnoses of depression. And then, of course, there are a whole host of other sociodemographic, health, and lifestyle variables that were collected as part of SHARE. So with that background, let's jump right into this first study of cognition-depression dynamics. So if we come back to this path diagram here, I've now highlighted this bidirectional association between cognition and depression, these two arrows. So this is really kind of a which came first, the chicken or the egg kind of study. We want to see if we can tease apart temporal dependencies between changes in cognition and changes in depressive symptoms. Now, we know that, as I mentioned, they're comorbid. Across the later part of the adult lifespan, we tend to see decreases in cognitive ability coupled closely with increases in depressive symptoms or depression risk. But the question is, does one precede the other kind of on average? Now, why would we want to look at that? Well, there are a number of different causal temporal hypotheses, and that might influence treatment regimens, screening, etc. So one possibility would be that these things go together because they have a shared basis in some underlying neurological condition, such as cerebrovascular disease or some other neurochemical imbalance. And so that shared condition is what's driving changes both in memory in this case and depression risk. Alternatively, it's been shown that people who are depressed tend to experience subsequent cognitive decline. There are a number of hypotheses related to that. One that's been put out there is that long-term neuroendocrine dysregulation can affect or can lead to hippocampal atrophy, which in turn affects memory, but there are others. Alternatively, it's been shown that cognitive declines or cognitive decrements put one at elevated risk for depression. So in that case, cognitive loss would precede increases in depression risk over time. And there are a number of different hypotheses related to that as well. For example, poor cognitive control and associated behavioral changes might lead to behavioral outcomes that put you at increased risk for depression. So again, in this study, we're just trying to say, is there some kind of way to tease apart temporally changes in cognition and depression? For that, we need to use studies that model bidirectional associations concurrently. And so far, there have been very few of those done, even fewer that have used data from 3 or more time points. And the last study here highlighted in red is the one I'll be talking about now. So let's go straight to the statistical model. This is called a bivariate latent change score model and structural equation modeling framework. It is kind of intimidating to look at, but my goal here is to break this down for you so you can understand how it may be useful for thinking about these temporal associations. So in this model, we have 2 processes. Across the top, we have memory scores. Those are the little circles and squares with M sub 50, M sub 52, M sub 54. So memory at each of these ages from 50 all the way up to 90 in 2-year intervals. Across the bottom from left to right, we have another process that's depressive symptoms. So again, depressive symptoms at age 50 all the way up to age 90. And then of course, we have all of these arrows linking them. So at the far left, the M's and the D's levels and slopes, those correspond to what we would typically see in a latent growth curve model or a latent change model. They're long-term trajectories of change. So the levels refer to stable individual differences in memory ability and depressive symptoms. The slopes are these long-term, in this case, 40-year changes in memory ability and depressive symptoms. Then in the middle, we have these kind of crisscrossed red pathways, gamma sub M and gamma sub D. So those we refer to as the dynamic couplings. So those are the time point to time point or lead lag associations, time-dependent associations between memory and depression. So basically, those are showing memory at age 50, for example, is affecting subsequent changes in depression or depressive symptoms, and vice versa, depressive symptoms at a given age affecting changes in memory. So really, this model combines multiple types of change, both long-term trajectories and stable individual differences, as well as this lead lag or time-dependent type of change associations. As you can imagine, it can be a little bit difficult to interpret, but we're really focused on these lead lag associations in the middle. So when we fit this model to our data, we typically do so in 4 steps. First, we fit a submodel where we leave out those time-dependent or lead lag couplings. And we just estimate the overall long-term trajectories of change in both processes. And then we add a single coupling. So in this case, it would be looking at the effect of memory at a given age as predictive of subsequent 2-year changes in depressive symptoms. And then we fit a third model, which has the complementary coupling, in this case, depressive symptoms at a given age predicting subsequent changes in memory. And then for a fourth model, we're fitting both of these couplings. So maybe there is some kind of mutuality going on. So we fit all 4 models to our data, and then we want to compare overall model fit to see where the evidence is strongest. Now, I'm just jumping straight to the results here. So there are 2 sets of 3 models each. I just mentioned that we typically fit 4 models. So why are there only 3 models per set? Well, that's because the model with depression at a given age predicting subsequent changes in memory, that simply failed to converge. It was not a good model for these data. There are 2 sets of 3 because in the first set, we just looked at memory and depressive symptoms in isolation from other covariates. And then in a second set of analyses, we included covariates such as assigned sex at birth, education level, tobacco smoking, BMI, and retest effects for cognition. So what this table is showing are just basic fit indices from structural, typically reported in structural equation models. But really what we want to do is run these likelihood ratio tests to compare changes in model fit as we're adding these dynamic components to the model. So with and without covariates, this series of analyses showed that the best fitting model was basically the one that had both the long-term growth parameters, but also this memory preceding changes in depression coupling effect. In other words, this gives evidence that lower memory or poor memory at a given age was predictive of subsequent 2-year increases in depressive symptoms across all of these 2-year intervals from age 50 all the way up to age 90. There are a few things I'm not showing here because of time constraints, but one more interesting piece of information about this is that dynamic coupling effect was actually strongest in middle-aged adults. So people who showed earlier problems with memory tended to show larger increases in depression across those 2-year intervals, or stronger coupling, I should say. So they had a stronger association between, there's a stronger association between early memory loss and subsequent increases in depression risk. All of which is to say, this is kind of a basis for wanting to be able to detect memory loss as early as possible in the lifespan, and also to realize that we may have a 2-year, possibly longer interval after detecting those lower memory scores to act on secondary depression risk related to that. Okay, that was a mouthful, and now I'm about to give you another mouthful because now we're going to jump into another paradigm. So in that prior study, it kind of gave evidence that we should be thinking about memory loss as a precursor to changes in depression risk. So for this next study, which is currently in review, we looked at depression or depression risk as an outcome, but now not just of memory or cognitive variables, but with a whole host of other predictors that may or may not interact with those cognitive declines. And I'll show you a list of what those predictors are in a moment. There are 56 of them. Coming back to this pathway, now we have all of these arrows kind of feeding into depression because that's our outcome. So we have both modifiable and non-modifiable risk factors. We also have their interactions, including with cognitive measures, all going in to predict depression risk. So quite complex. Previously, most studies that have looked at comparative risk factors or protective factors for depression have really relied on meta-analyses. And there have only been a few studies, at least with large population representative samples, that have taken a machine learning approach. Both of those that had been published at the time of our study were applied to data from UK cohorts. So to my knowledge, this is the first study to use machine learning to evaluate numerous predictors for depression risk in middle-aged and older adults outside of Europe. You may or may not be able to read what these individual risk factors, protective factors are. Mostly this is just here for effect to show you that we looked at a lot of them concurrently. Something that would be difficult or impossible to do in kind of standard regression analyses, for example. So again, we had 56. Roughly, they can be broken down into 3 categories of variables: demographic and family-related predictors. So chronological age, country of residence, education, employment status, number of family members, et cetera, et cetera. Social network and transactional variables. So that was a nice feature of shared data at Wave 6 as they collected a bunch of social network information. So number of people in your social network, average emotional closeness to people in your social network, distance to people, physical distance to people in your social network, self-rated loneliness, etc. And then we also have some health and functional limitation related variables. So number of chronic diseases, Cher has a list of those that go into that count. Self-rated poor health, hypertension and diabetes, which are both related to cognitive decline and depression, as well as body mass index. In fact, body mass index, we found previously using this machine learning technique to be the single strongest predictor of dementia in the US version of this study, the health and retirement study. Smoking, physical activity, and then several functional measures as well. Fine motor skills, problems with mobility, problems with activities of daily life. And then 3 cognitive measures. So again, we have delayed recall memory, but for this, we also included a measure of numerical ability, which is kind of a crude measure of what we call fluid intelligence or abstract problem solving. And then orientation, which is just a basic measure of cognitive status. So with so many predictors, how are we supposed to really evaluate their comparative importance for a given health outcome? We're not just going to throw them all into some giant regression equation soup, I hope. One reason for which is multicollinearity. When you have predictors or variables that have a lot of overlapping predictive information, when they're in the same regression model, they can compete with each other and you get kind of odd results based on that. These variables and risk and protective factors probably also interact in complex ways to influence depression risk. So if we were to include all of the interactions as well, you can imagine how unwieldy that regression equation might look like. So we really need a more principled strategy for sorting their respective predictive influences apart. And for that, researchers, particularly in medical fields and in epidemiological research, are relying on machine learning approaches, and there are a number of those. So the machine learning approach that we typically have used is known as random forest analysis, which I'll now explain. So random forest analysis is extension of regression trees. So for a regression tree, basically how that works is you're taking all of your observations and you're trying to identify the variable. So I guess let me back up a second. The first thing is these trees are kind of like upside down, right? So they branch out and each branch bifurcation is referred to as a node. And so the top node, for that, we're looking at all of the observations in our data, and we're trying to find the variable that best distinguishes whether or not someone is depressed at this particular time point. So if it's a categorical variable, for example, if it's biological sex, then if that's the best predictor, then you would then separate that sample into women and men. If it's a continuous variable, let's say how long someone has been a smoker for, then you would find the cut point of that continuous variable. So let's say it's smoking for 10 years versus not having smoked for 10 years, and you'd split the sample on that. So now you've split the sample at that top node. Now within each of those subsamples, you're going to do the same thing. You're going to look for the best predictor, and so on and so forth, all the way down until you have, 30 or 50 or 100 individuals left in those bottom, well, they're referred to as leaves with the tree metaphor. And then that basically gives you a sense of, well, at the top level within everyone, our best predictor was whatever it was, but then within subsamples, other predictors may be more meaningful. And this tree-like representation is quite powerful because it actually captures interactions between variables, because you have variables that may be predictive in one subset of individuals in a certain way, and predictive or not predictive in another subset of individuals in a certain way. So that's quite powerful because you don't have to actually model all of those interactions directly, which would be almost impossible in just a typical standard regression setting. However, a single tree approach is not ideal. This is related again to the problem of multicollinearity, because let's say at the top node you have two predictors that are both really strong ways to identify differences in depression risk, but the computer may just preferentially choose one over the other, even though the other one's also really good. And the resulting tree after that initial choice could be totally different than it would have been had that other predictor been chosen at the top level. So it's kind of a spurious selection effect, basically. So these trees I'm showing you here, kind of example trees at the bottom of the slide, they're all created from the same data. And you can see just visually how much they differ every time you kind of rerun this. So with the random forest, we understand that a single tree probably will be unstable in its representation. It might not replicate were we to run it again, not just on our own data, but in a new sample as well. So a random forest, per its name, creates a whole bunch of different regression trees, but it does so in an interesting way. It subsamples observations for each tree. So it's not using your full observations for each tree, it's just using a subsample of them. And then it's also taking a sample of your variables at each node of the tree. So what that confers two benefits. By taking subsamples of observations that are different for each tree, that allows for built-in cross-validation. So you can kind of, with different samples, confirm over and over and over again what the important predictors are by resampling your own data, similar to bootstrapping. But then also because you're sampling variables, if you have two variables that are closely linked, maybe multicollinear, or maybe they're both strongly predictive and they're competing, well, because they're being randomly sampled, they might not always have to compete with one another for that place of importance in a given tree or at a given node. So once you've created this whole forest of trees, then you have to summarize the variables, locations, and importance for prediction across all of the trees for the forest. And that gives you this variable importance estimate for each of the predictors that you're looking at, or VIMP. Again, I know that's a lot of technical, there's a lot more, but I'll leave it at that for now. Bottom line is this is a very powerful method and a robust method for comparatively looking at predictors of a given outcome. Okay, I've mentioned all this, so I'll skip past this and jump right to our results. So out of those 56 predictors, these were the top 10. Notice also that we ran these analyses disaggregated across men and women. The reason for that is, in general, women show 2 times the prevalence rates for depression following middle age that men do, and it's not exactly clear why. So what's striking about this particular result is that the same predictors show up both for women and for men. The top predictor being social isolation, second, self-rated poor health, and then third, difficulties in mobility. Social isolation and poor health are both subjectively reported. So there is the question of, well, what is social isolation related to? We have all of these social network variables. Well, it turns out that of the objective measures, social isolation is actually most closely related to whether or not your partner or spouse is still living in your house, or whether or not you have the person who's emotionally closest to you lives within a 5-kilometer radius from you. So it's really about whether or not your closest attachment person, closest emotional person lives with or near you. Also on these lists are a number of other functional measures. Notice that mobility, though, shows up above activities of daily life or fine motor skills. And also numerical ability shows up on both lists. So that, as I mentioned, that's a measure of fluid intelligence or problem solving. That tends to show up in depression risk quite a bit. And one other piece of this that I didn't mention due to time constraints is that we actually ran this in a split sample validation framework. So we took that original sample of 67,000 individuals, we split it in half. In the first half, we used that random forest analysis approach, but then based on the top predictors identified in that, we brought those into a stepwise logistic regression framework, and that allowed us to estimate in a conventional statistical model the percent explained variation of these top predictors. And so overall, these top 3 or 4 predictors explain about 24% of variation in depression risk for both women and for men. As I mentioned, they're almost identical. The top 3 predictors are identical for women and for men, but it turns out there are also some slight differences, about 1 to 2% of explained variation. For women, that was related to burden of providing care for family members, and for men, it was related to difficulties in performing activities of daily life. So there are some distinguishing characteristics across the sexes there. Okay, so just to wrap up, we use these 2 kind of heavy-duty statistical approaches. In the first study, we were using it to look at the temporal dependencies between cognition and depression. And from that, we found that yes, cognitive declines over the long term and increases in depressive symptoms over the long term, those go together very closely, but we could also tease apart this other time-dependent effect where lower cognitive ability at a given age predicted 2-year increases in depression risk. So that does provide some incentive of trying to detect cognitive decline or cognitive loss earlier in order to prevent secondary depression risk related to cognitive decline. And then in the second study, we used that machine learning approach, random forest analysis, to look at a whole host of risk and protective factors related to depression. And for that, again, social isolation, poor health, and mobility problems showed up to be the top risk factors. So these are both very relevant outcomes for problems, mental health problems affecting older adults, which we were able to arrive at using these sophisticated statistical techniques. And having said that, I just want to acknowledge my colleagues, Paulo Gisletta at University of Geneva, Elizabeth Handing and Jesse Chow here at Colorado State, Carolyn Strobel, who's an expert on random forest analysis at Zurich, and then Leilani Feliciano at Colorado Springs for their help on this work. And also to just acknowledge financial support from the Swiss National Science Foundation for the first study, and for startup research funding from Colorado State for the second study. So thank you.